Welcome back, everyone. So next we have Narendra, a CTO at DK AI Lab. He will be presenting Hominis, training human-centric large language models. In this session, he will introduce Hominis, a groundbreaking family of LLMs designed with a focus on human centricity and environmental responsibility. Narendra will share insights into the development process, including scaling challenges and innovative solutions, as well as the role of the Leonardo supercomputer in enhancing Hominis capabilities. This session will conclude with a live demonstration of Hominis in action. Please welcome Narendra.
So, hello everyone. Again, I'm Narendra Patwardhan. I'm CTO of DeepCafa AI Labs, and I'm here to introduce you to the notion of human centricity in AI and how we used it to train Hominis, one of the EU's first foundation models. This talk is divided into 5 segments. First, we will go into the motivation about why human centricity is important. Then we will go into the design decisions that go into it. Later on, we will go into the training tricks required to make it scale well. And if time permits, then we will go into extensions and how to make the most of your text-only models. So first, in 2017, transformer models were popularized, and it changed the way that we view deep learning. Stanford AI Labs tried to codify that into foundation models. They call foundation models as any model that has been trained on broad data and which is applicable for a broad spectrum of downstream tasks. So the decision factors are the scale of the model as well as the task spectrum that it is applicable on. And some of the examples of that are BERT or CLIP. We felt that this definition lacks to be a true foundation. So we introduced the notion of human centricism into it. We call a human-centric foundation model as any foundation model that aims to minimize the environmental impact that it has while fostering innovation through open access. So for us, the decision factors are sustainability as well as the extensibility. And some examples of that are Llama and now Hominis. Let's go into why we needed to add this notion of sustainability or extensibility into it. While from 2018, the scale of the models has been exponentially increasing, we are finding that it is ending up into diminishing returns. Also, when you extend the scale of the model, you have to carry out a hyperparameter sweep, which leads into more environmental harm and increases the divide between the haves and have-nots. We also feel that a truly open foundation model needs to be open and not only be accessible through APIs, because that restricts the things that you can do with it. So it cannot be a true foundation. We also believe strongly into the open source ecosystem and the environmental impact that it brings. Now that we know that what's a human-centric foundation model, let's go into how to make a transformer-based architecture based on those principles. First of all, you have to choose the right transformer variant, and there are 3. You could train an auto-encoding model, which projects the sequence into a fixed dimension. You can train an auto-regressive model, which only attends to tokens that it has seen in the past. Or you can combine those two and train a sequence-to-sequence model, which first projects a sequence into a fixed dimension and then carries out auto-regressive decoding on top of that. Now, on modern hardware, auto-regressive models win because once you feed a sequence of length n to auto-regressive models, they also learn how to attend to all the subsets of sequences before it, which is a truly marvelous advantage of auto-regressive models, and that's why they have been winning over the course of last 5 years. After that, you have to choose the right attention variant. Attention is a fundamental block of all transformers, but it is costly to compute. So you have to choose the right variant to minimize the environmental impact. And there are like a couple of ways that you can do that. First of all, you can use any kind of linear approximations to minimize that impact, or you can replace the attention matrix with just some synthetic matrix instead. Or you can utilize the I/O patterns of the hardware so that the attention is computed in a faster manner. We carried out ablation study over all these variants and found out that acceleration via I/O awareness is the best one. The next one is choosing the right projection variant. Over here, it's kind of easy. The first one is your standard linear layer, which is just a matrix multiplication. And the second one is mixture of experts, in which first a router chooses which projection matrix to go to, and then it's just a matrix multiplication. Now, as you can rightfully think, that mixture of expert is the better one, and through ablation, we found the same thing. It is not parallelizable well on modern hardware. So you have to go for a linear layer. But fortunately, once you train using a linear layer, you can convert that into a mixture of experts layer quite easily. So you train with a linear layer and convert into mixture of experts. Now that you have the fundamentals of model, you have to decide how that model is going to consume the data, which is done through tokenization. So once you have a sentence, there are a couple of ways that the model can consume it. The first one is a vocabulary-based one, which cannot handle the words that are not part of the vocabulary. The second one is the subword one, in which you break down the words into subwords. But this cannot handle characters from different languages or non-Latin languages. The third one is byte-based one, which is one of my favorites when it came out. It just uses raw UTF encoding and utilizes the bytes directly. However, UTF-8 requires 1 to 4 characters, so whatever is the number of letters gets multiplied by approximately 3.5, and this is not desirable. So the best one, in my opinion, and through ablation, is byte pair-based, in which you utilize the first 255 bytes as a fallback, and then merge the most commonly occurring bytes together as a new vocabulary. So we go for byte pair-based. Now that we have the model, we have to choose the right scale of tuning it. The first factor that goes into it, if your model will fit on a consumer-level GPU. Because at the end of the day, you want more people to use it, and consumer-level GPUs are everywhere. So you have to make it fit on, let's say, NVIDIA RTX 3900 or something like that. And you have to make the model distillation-free. When you train a model from scratch versus when you train a larger model from scratch and distill it down, the second variant is known to perform better. So the model has to be distillation-friendly. And the third one is that it has to be equal in training and inference. If you train a larger model, then while carrying out inference, the cost is much higher. So you have to make like a middle ground between the sizes. And based on these factors, we found out that 13 billion is the optimal model size to be trained on modern HPCs. Now that we have the model, we go into data sets. We want to have a data set that is completely permissive so as to avoid any legal issues and to be truly human-centric, because we don't want to infringe on anyone's copyright. So it has to be permissive. It has to have a good source quality and deduplication, because if you have multiple sentences which are similar, then the model is not actually learning anything new. It's just seeing the same stuff again. The third one is multilinguality. The model has to learn more languages than just English or whatever is the popular in that country, because there is a cross-language bleed of capabilities. And the fourth one is data coverage. It should not only come from Reddit, which is what the first GPT models were based on, because Reddit is a toxic cesspool. And you have to have different sources, such as newspapers, modern research articles, or code to make the model actually useful for downstream applications. Based on these factors, we found out Red Pajama v2 is the best modern available data set, which follows all of these factors. Now that you have your model and your data set, we have to make it scale on modern HPCs. And so we go into the training tricks required to do so. But before, we have to go for augmentation of the same data. Because the data comes from diverse sources, you cannot be sure that it is properly curated, even though they provide curation metrics. So you have to augment with some data that you have created. So we carried out scraping of GitHub as well as Archive, which are scholarly sources. And we carried out heuristic-based filtering on top of that. For GitHub, we based that on number of stars, if the repository had commits in the recent times. Whereas for the scholarly articles, we used if text is available as source, and then if the particular researcher, which is mentioned in that paper, has enough H-index or citations to make it really useful. So we converted that into a data set called Hominis Reserve, which we used to augment Red Pajama v2. The next is utilizing mixed precisions. If you were to train a model, it is usually in parts of like FP32, which takes 32 bits to represent any single data point. Whereas if you train with something such as FP16 or BF16, then you get a little bit less precision, but you require much less amount of memory to load it on your GPU. We found that BF16 gives us reduced memory by almost 50%. So we trained with mixed precision. This is an option that you can utilize in most modern deep learning frameworks, and it's just one click, and then you reduce your memory usage by 50%. The second is gradient accumulation. When training with large amounts of data, you cannot make it fit at a certain time in a batch on the GPU devices that you have. So we utilize gradient accumulation, in which we divide the data in multiple chunks, and each chunk is retained with its gradients. Afterwards, all the gradients are accumulated in a single step, and then the update happens, instead of having it iteratively. There are some more tricks, such as gradient checkpointing, in which instead of computing and storing the activations, we do it again using backward pass. So you trade a little bit of computation for memory. And this makes you train with much larger models than you can, which is up to root n. The last one is FSDP, or fully sharded data parallel, which is a workflow orchestrator that divides the model in an optimal manner, or divides model, data, and as well as activations across all the available devices in an optimal manner. All these tricks are just one line of code in modern deep learning frameworks. Now we added something new to the mix. We added a Git-based workflow in which we use LoRa, or low rank approximation, in which a matrix can be represented instead of its original dimension as a multiplication of two different matrices of much smaller sizes. So let's say if you have M into N matrix, you can represent it as M into R and R into N, where R is significantly smaller. This gives you a reduction of almost 100 times in memory. We utilize the low-rank approximation matrices using a Git-based workflow like this, in which we first copy all the original weights on each GPU, and then we instantiate one LoRa on each GPU, which learns a smaller representation of the data that it is currently being trained on. We then commit all those LoRas together into one LoRa, and then add back to the original weights in a merging step, so which is just what Git does for code. Now that we discussed the methodology to train a human-centric model, we trained Hominis Core 13b, which is a foundation model that performs on par of Llama with 50x less carbon emissions, and it outperforms Llama 2 on everything. The reason that we are using Llama 2 instead of Llama 3 or later versions is because Llama 2 is the last pre-training only model. But we have also instruction-tuned the same model, and we have made it available at hominis.io/playground for everyone. If you want, you can reach out to me at the email ID that I'll show at the end, and you will get access to it. We are currently comparing it against the closed source variants, such as Claude or ChatGPT, and the initial response from our consumers is quite positive. Since we do have time, and I rushed through it, we'll go into extensions. So how to make most of your text-only models. The first is inference optimization. And I believe the next talk after me is going in more details about this. But this is one of the key steps that we use to make our model fit on consumer devices. Like we saw earlier, that how the mixed precision arithmetic reduced the memory usage by almost 50%, you can actually reduce the precision even more during an inference step, and the accuracy loss is quite small. So we use a format called Q4M, which reduces the memory usage by 87.5%, and that makes it fit on a single NVIDIA GPU, any NVIDIA GPU that has more memory than 4.5 GB, which is most GPUs nowadays. And we also created our own framework based on MLIR, which is ML intermediate representations, that fuses multiple kernels together so that the inference is fast. Once you have fast inference, it opens doors to new applications. And people want to not just use text, but other like methodologies, such as utilizing images and asking questions about them, or utilizing videos and asking questions about them in natural language. How to do that is traditionally with retraining the entire model from scratch in a multimodal way, or retrofitting an encoder. But we wanted to introduce methods which can do without like retraining or utilizing much more like resources. So we introduced the concept of post-hoc multimodality, or how to extend the model capabilities without significant retraining. There are two approaches that we have came up with. The first one is code as intermediate modality, in which our text-only model produces a DSL-based code, and it has been restricted to produce only that DSL. That DSL is a function calling DSL in which you can like add functions such as find in image or count, and so on. And then we generate program score pairs. The best performing one gets like executed inside a container, and whatever is output is the question that the user asks. So this can be used to extend a text-only model to image understanding as well as image generation, and we are working on video capabilities right now. The second way that you can extend is using BNF constraints. BNF is Backus-Naur form, which is the way that you can formalize grammars. Once you restrict the access to the text-only LLM through APIs, you cannot do that. But if you have access to the weights, you can control the sampling strategy. Now, normally the sampling strategy is just a greedy, like tree-based search, in which you get the most probable token. But if you restrict with grammar-based sampling, then you can have a JSON output, or a YAML output, or an output in the DSL of your choice. So you can restrict it to call only the functions that you want, and through that, you can make any external function call. So you can make like the language model move a robot, or synthesis voice, and so on. So it increases its capabilities by many folds. And that's about it. So I think we will have a lot more time for questions. So thank you.
Thank you for a very nice presentation. Thank you for your presentation. It's very inspiring. I have a question. What time actually did it take to train this Hominis model? How long it take, and on what configuration? So okay. If it is possible, maybe to retrain it on our data using LoRa mechanism, yeah. Or if it is licensed, or how does it work? So okay. There are two questions, actually.
Yeah. So first of all, how long it took us for training it. Tari Singh is here. He is the CEO of DeepCafa. He announced that we got the grant to train it on Leonardo, which is the 5th largest data center in the world, and 3rd largest in EU, last year at DSC. And over the course of last year, we trained this model. So we trained 2 models. First is raw, which took 8 months, and then the instruction tuned, which took 4 months. On 32,000 GPUs, so it's a lot. But it is doable if you have access to high-performance computing. But the thing is, this model will be released with Apache 2.0 license, so you don't actually need to train one from scratch. You can just build on the efforts that we have made. Also, if people don't have access to HPC computing to fine-tuning it, we are also launching a platform called Hominis CI, in which you can just like bring your data, and we will train it for you. So I think that answers your question. Anyone else?
So maybe you said that, but like I entered a bit later. Like, did you use any model parallelism? If I'm not wrong, then probably no, because these small models would fit on the machine. Yeah. And then you just basically did the data parallelism on this 32K.
No, we use fully sharded data parallelism. So we like parallelize the models as well as data and the activations while carrying out the forward pass.
Okay, thank you.
Could you expand a bit more on the highest level of quantization that you showed, the one after FP16?
So they don't have my presentation over here anymore, but the highest level of quantization that's possible is binary, but that usually results into more than acceptable loss of accuracy. So usually we go for Q4, which is quantization to 4 bits. And it performs quite well. Like, it performs on par of BF16 in inference, not during training. The binary like neural networks are something that is coming out now. It might like gain popularity because you can fit on, let's say, mobile phones. And we have some efforts into doing that. But we find that it's much better to train a larger model and then quantizing it to Q4 or distilling it down to a smaller size and then quantizing it to Q4 rather than making it Q2.
Which types of limitations do you usually get with that type of quantization?
Well, it's just loss of accuracy because it gets, let's say, recursively added through each layer. So you have some loss of accuracy in layer 1 that gets like propagated into layer 2 and so on. And if you have, let's say, 64 layers like we do, then that loss is like too much, so the end results are not good.
Thank you.
But in terms of percentages, I would say binary neural networks usually go for like 15% reduction in accuracy.
Any more questions?
I think that's it. OK, thank you, everyone.